Okay.
So, hello, NetPaths. And today we have Naomi Arnold here. She's a postdoc in London, and she's going to talk about temporal graph motifs and how to find them. So please, Naomi, when you want.
Lovely, thank you. Thanks at least for the introduction and for the invite to come and speak today. It's I think the NetPost is a fantastic initiative. And uh, yeah, it's nice. We used to do something sort of slightly similar within the Queen Mary Networks group, but to see something like cross universities is really great. For the talk today, I'm going to speak about some work which is work in progress. Hopefully, very soon have something on archive to share about, but it's relating to temporal graph motifs, specifically applied in a cryptocurrency context. And in the spirit of the NetPlace theme, I'm also going to talk in the second part about some of the challenges relating to the scale of the data and getting the algorithms that I was interested in to actually run on such a large data set. But yeah, as it's work in progress, but please feel free at the end if you have any feedback or comments just to get in touch about it. I'll discuss afterwards. So just a little bit of background about myself. Right now I'm a postdoc at the Northeastern University in London, in the Network Science Institute, but before my background was in mathematics, which is what I did for my undergraduate. Then after this, I got interested in the idea of the networks and complex systems and ended up coming to do my PhD in the computer science department in their networks group at Queen Mary. And during this time, I got into my PhD theme was on modeling networks that grow in time. And through this, I developed a code base called Theta. Then towards the end of my PhD, I got involved in the Raft3 project, which is going to be some big theme of the talk today. And this was a platform written by the gentleman sat next to me as part of his PhD, but then became a wider project as a software for analysing temporal networks. And this ended up being taken into the first postdoc at Queen Mary through the Alan Turing Institute, where we're looking for temporal network use cases and different data sets that we could study. And the Raft3 project has also been spun out into the company Pometry, who do some consulting on top of the Raft3 software. So just a little quick piece about Raft3. Raft3 was built as possibly the first platform with large and temporal networks in mind. So what you can do in Raft3 is attach data from anywhere, whether that's something that's a CSV on your machine or a data stream from somewhere. You tell Raft3 how you want to visualize, how you want to convert that into a temporal graph. So updates of when nodes or edges are added and removed. This is then stored as a distributed graph with a log of the full history of properties and structure of nodes and edges. And then the user endpoint is provided for then performing a different analysis on the graph. So there are about 30 different algorithms implemented out of the box, with many of these being sort of the classic static graph algorithms, like different centralities, performing cascades, similarities, but then some much more temporal focused ones, like the motifs, which I'm going to talk about more in detail today, or temporal community detection methods. So the application of Raft3 we're talking about today, which is my work at the moment, is studying temporal motifs in a cryptocurrency context. So the specific part of the I guess, cryptocurrency ecosystem that we're studying this was a dark web marketplace called Alphabay. I wondered, has anyone heard of Alphabay before, or other ones like Silk Road? And I know you have, Ben and Richard. But Alphabay was a site on the dark web where people could buy possibly mostly illegal things like drugs. I think there were some listings for guns, stolen data, or means to commit cybercrime or fraud. And it was shut down. It was launched in 2014 and then shut down in a big sort of undercover operation with the FBI in 2017. But as from a network point of view, to buy and sell on Alphabay, you used Bitcoin, and Alphabay acts as a sort of middleman for you could make purchases directly to someone else, but a lot of the time you would purchase through Alphabay, where you'd send it to them as an escrow, and then they'd send it to the seller of the goods. And the data set that we were using were all users or entities who'd ever interacted with Alphabay market and their transactions. And on temporal motifs, what we mean by a temporal motif in this instance is a small subgraph whose edges are ordered, both directed and ordered in time. And we also specify a time parameter delta, which constrains the time in which the motif has to complete. So means that the difference between the last edge of the motif and the first edge of the motif has to be less than delta. So if this was the motif that we were looking for in the network, then this would be it would be an instance of that motif because the edges are all in the right order, and the difference between the first edge and the last edge is less than 10. However, this one wouldn't be because the difference between the first and last edge is greater than 10. And then this one also wouldn't be because the edges are in the wrong order. And what motifs are we looking for in this data set, and what do we hope that they might tell us? So we restricted our focus to motifs which are happen on 3 edges and involve up to 3 nodes, of which there are quite a number of them. And the algorithm that we use is from this paper called Motifs in Temporal Networks a few years ago. And some of the different types of motifs that we have in this big grid of possibilities it includes motifs that happen just between 2 nodes. So it's, for example, that's me sending someone 3 separate transactions of Bitcoin or back and forth ones. We have motifs which are all outgoing from 1 node, so it might represent some fanning out of money, or it could be some mixing service that's splitting a transaction across multiple wallets. We have the other way around as well, where someone's receiving transactions from 2 different sources. And there are other more complex ones like triangles in here, or mixtures of receiving and sending between 2 nodes. And our experiment was we had this data set of which there were, I think, 11 million users represented, and then 33 million transactions, which is quite a large network as far as they go. And the local motif counting algorithm that we implemented in Raftery, in the end, and I'll talk a little bit about the journey in the second half, it took 2 hours in total to build the graph, and run the algorithm on top of it. So to give a sort of first glance of the motifs that we see in Alphabay, we'll show this grid, and we restricted this to motifs that complete just within 1 hour. So focusing on quite short range patterns in the data set. And the way that these are enumerated is the column down here shows the first 2 edges of the motif, and then the row shows the last edge of the motif. So for instance, this one is someone sending another person 3 separate transactions. And we see some quite striking numbers of motifs that are in the trillions and hundreds of billions in some other parts. But the most prevalent type of motif is this fanning out. So someone sending money to multiple different sources, which could be that could speculate as to, is it someone a service on the blockchain that's splitting money across transactions, or and then the next most common one is 3 transactions in one direction, all between the same pair, and then finding the third most common type of motif are the all incoming patterns as well. So our next question for this as well, that's obviously a huge number of motifs in the network. What does that look like if you look at the motifs that different nodes have, and what the spread is like? And we found that merging the motifs into sort of different categories just to make things slightly easier to make out, we've found that all the motifs were quite very heavy tailed in their distribution. So there's 1 or 2 nodes there who have trillions of motifs which are all outgoing, and in fact, when we're having restricted to this 1 hour period for motifs to complete, there's I think only 1 million out of the original numbers of nodes that are represented as having motifs in the data set. The next interesting thing we found was that if we looked at just the top nodes in terms of the numbers of motifs to see where those motifs were concentrated, these being the top 2 nodes in the data set, we find that those are actually very different in their motif spread. So this is the top node who has trillions of outgoing motifs, but the next one down, it has its motifs are much more concentrated towards receipt of money. So the first one, we need to investigate this more, but it could be a mixer service, or it could also be a crypto on-ramp where people pay with real money and receive Bitcoin from this entity. And then on the other hand, this node could be an exchange where people send it crypto to receive real world money, or it could be a big seller on Alphabay. And interestingly, the Alphabay market node, which has by far the largest degree in the network, is not even represented in the top 10 in motifs. And that some of the motifs that we see in the Alphabay market node are precisely the motifs which are consistent with it being an escrow service, where it which has mixtures of receiving and then sending money out to different users. Our next thing we looked at was studying motifs over time. So while the previous results were just looking at the whole network, the motifs that completed within an hour. But in this part, we looked at still the 1 hour motifs, but batched by month, and how both the number and composition of motifs changed over time. And just annotated on this left graph is the dates of when Alphabay market was launched, and when it was dissolved again. And here we see a huge spike in the motifs, all mostly being outgoing. Someone sending out money across 2 different nodes. But I think one interesting thing here is that the motifs had a very, very sharp downturn long before the Alphabay market was shut down. And the shutdown of Alphabay was something that, as far as we know, no one in the network knew about it, because it was very, very undercover as an operation. So I don't know if it's perhaps a change in a service that happened around that time, or some particular service got shut down. They need to possibly investigate more. But then another interesting thing that we find is that if we look at the composition of which motifs are the most common over time, before they formed in this period, it's mostly dominated by this green and blue, which represent motifs that just happen between pairs of users. So perhaps user pairs which have been established before the forming of the market. And then when Alphabay comes in, this switches over almost totally to the most star-like motifs, which could represent the use of services to make transactions rather than people making direct transactions between users. And again, this is something that persists, the dominance of the star motifs, quite after Alphabay is shut down. So to finally look at some sort of future directions of where we'd like to go with this work, is that with this focus on local motifs, so the motifs that each node has, we can represent each node in the network as a vector of with I think 36 or 40 dimensions of the numbers of motifs that they have. And we've performed some early experiments looking at them, how you can cluster those nodes based on their motif types. And we found that they do seem to produce sort of fairly salient clusters of users with similar motif patterns, which we hope might be an interesting tool that people can use to possibly see if there are different types of users or services on within the cryptocurrency ecosystem based on their motifs. So for the next section of the talk, I was going to talk a little bit about some of the struggles and challenges of working with big data. But first, I just wanted to pause to see if anyone had any questions about the work itself.
Yeah, if someone has any question on this part, can go on and make the question, because it seems that there are no questions. Maybe people are still processing.
Yeah, no.
I have a small question, like in the slides before,
Yeah, sure.
where you were showing the downturn of this one, for example.
Yeah.
So yes, you see that it goes like the scale is 1 to the 12 to the power of 12.
Yes.
But does it like like what is the scale after this 2017 shutdown thing?
I'm
Because
trying
you
to
cannot
remember
see.
now. Yeah, because when we did have
Because
some
it's not
plots of
zero. It's gonna be also a big number, but I'm curious to see how maybe with a logarithm scale would be easier to
yeah.
see.
I was really torn because we actually made a plot with a logarithmic scale on it initially.
And then I screamed, "Don't do that, Naomi."
No,
Yeah,
I understand.
yeah,
I understand why you
because of
did
the
it.
stacked a big because it's showing things stacked on top of each other. But I think
Yes.
maybe
Yeah.
some plot with just the total number of motifs or the comparing the numbers of motifs but not stacked on top of each other might be a good way of showing this, because it's
Yeah, no, it's always
would
tricky.
be
I understand. But I'm curious to see how it grows in time in general, the scale of the motifs that you see. Also, depending on the number of nodes that you have in the system, you know, if it
yeah,
scales with the nodes. I mean, maybe you have more motifs because you have more people doing transaction in general. It's not, it's like a scale you can, I don't know. I'm just curious on all these
yeah.
things, how they scale up, you know.
I think so something quite interesting I'll just okay, I'll answer that question in a second. But when we had another plot, which I maybe should have put that on and said that had the number of transactions over time, because we were interested in sort of is it just reflective of there's a lot of transactions in the network, so there's a lot of motifs, but the transactions remained so they were on a different scale. They weren't anything near like went into the 12, but the transactions remained high right until Alphabay was shut down. So it seems to be capturing something more complex than just the sort of numbers. And similar with when we correlated the number of motifs it has with the degree of the node. Whilst there was you know somewhat the relationship of if you have a higher degree, you have higher motifs. There was like crazy variation between if you had degree 10, you might have 100 motifs, or you might have a few billion motifs based on but when those transactions happen in time. So yeah, but thank you. That's a really good point.
Actually, I have another question.
Yeah, of
If
course.
I can. Just one last one. In general, like also, could it be that maybe there's been a change of the time step? Like you have 1 hour delay in the temporal graph that you're considering the motifs in. Maybe just change the time scale of the transactions, you know? I don't know if it's a thing. I don't know if a lot on this, but
Yeah,
curious.
this was something that we were also considering, which it seems not to be the case, but there is with Bitcoin transactions, it takes about maybe about 8 minutes between you make the transaction and then the transaction actually appears on the blockchain. So I think that can end up delaying some of the motifs which involve back and forth between because if you're making a decision on what to do afterwards, depending on receiving one, then the time it takes to complete, say, a sequence of 3 edges in that way might be longer. I've just seen a question in the chat from Funky that this data set itself is not not publicly accessible because it's from a partner who've done some entity resolution on the data. But one of the other data sets that PageE has been working with doing a similar type of analysis is the NFT OpenSea data of NFT purchases, and that data set is totally public. So shall I move on to the next part of the talk?
I think so, yes.
Cool. So yeah, in the spirit of the NetPlace theme, this part of the talk's gonna cover some of the challenges I had and what I've learned with working with big data, and the big question of why is working with large networks so damn difficult. And the first thing on this is that with big data in general, if it wasn't network data, there are many tools such as, I don't know if anyone's heard of Spark or MapReduce, which are good for working with problems that involve big data, and their principles are splitting the data up into sort of equal sized chunks, and being able to run something on those chunks and combine them afterwards. And a big example of that is the word count in MapReduce, where you can break a big text chunk into paragraphs. There's different, if you have a cluster or different cores of your computer, they do the word count on those chunks and then combine it all together. So there are tools for big data, but with networks, as the title of the slide suggests, there are just power laws everywhere, which makes splitting up those tasks or programs you've got to run them like very, very difficult. In the case of Alphabay, there was a node with degree, I think it was degree 1,000,000, just because it was the market node and receiving. And so even when you try and partition this problem into smaller chunks, there's always going to be one node in there that's got loads and loads of edges. And also, aside from the partitioning side, many algorithms in networks have a sort of worst case scenario if the network is a scale-free one with power law. So you find that it's just much worse than, say, if it was a random graph with everything similar degree. And on that theme, it's also quite memory expensive to store graphs in memory. As in, to give some numbers again, the Alphabay dataset was, as a CSV file, was about 1 GB, but when we were loading it into Rafterade, this expanded to being, I think it was 200. No, it was about 120 GB in memory to actually represent it usefully. And this meant that we were using Azure credits to have a big machine that could be capable of running it. And I spent probably a few weeks getting Java out of memory errors when the algorithm was getting so far, but it made the variables it was making to do so were too chunky. And then another thing on this is that the when you have an algorithm of a program running on network and it's very, very slow, I think the first time I actually got it to work at all, it was over 24 hours, and was that, yes, finally I've managed to get that and got some results. I brought that to the group chat that we had about the paper, and everyone was, of course, very excited. But then the questions come in very quick about, oh, what does it look like with a delta is 1 day instead of 1 hour? Or perhaps should we try it with the same thing with the top node removed? Or what about if you do it over these different time periods instead? And something I found is that if you have code that takes an awful long time to run, it curbs your enthusiasm for changing different parameterizations, and that I think it makes it worthwhile thinking about how to improve it if it's fallen into that that category. So onto what did I learn from this, and this was in terms of between getting it to first thinking of running the algorithm to getting it to run, and improving it down to much more nicer timescales to work with. It was maybe 2 or 3 months, and some of that process I just don't think I could have shortcutted because it was a learning experience long way. But there's definitely some sort of nuggets that I think would be useful if you're thinking of working with some larger data sets, or doing some very computationally complex algorithm on a smaller data set. And the first one would be to get a crash course on data structures. Myself, my background wasn't in computer science, and when I was learning how to program, it was for the main aim of just getting things done. So learn probably as minimal as I needed just to get the a program to run and be fine, which was is okay for a lot of scenarios. But then when you need something to run efficiently, or on large data sets, that's when you sort of need to maybe start thinking about this. And one thing that was really important in this work was getting the right data structures there. So I'm not sure if you're familiar with big O complexity, but there's when you make a collection in whatever programming language you write, whether it's in Python or Java or something, they each have different properties of in terms of how fast it is to access something from that collection, or adding something in, removing it, scanning it, and it's worth thinking about which one you're going to use. So, for example, if you wanted to if you had a list and you wanted to access a specific element of it, then that operation would sort of scale by order n, so the size of that list. And one of the first times goes I had writing this algorithm, it was the algorithm itself was order n squared, which is not amazing, but it's okay. But because I'd used a list instead of a better data structure, I'd inadvertently turn it into an order of n cubed algorithm because it was spending all the time looking for different elements in that list. So when having read something like this, or learned a little bit about the data structures to use, you gradually grow the instinct of when you're making something that involves a collection of whether that's strings, integers, doubles, you can start thinking, say, do I know its size beforehand? Do I need to add or remove things from it? Do I care about the order that the item's in? Is its purpose for checking if an item is in that thing? Maybe you want to use something like a set. And will you be accessing specific items from that list, or will you be wanting to just access the start or end element? And being able to just know what some of those operations are like and ask that when you're writing code, it can make the journey a bit smoother for optimizing code. The second thing that Richard taught me quite early on in the PhD and has been really worthwhile is learning how to use and interpret a code profiler. And there's usually two types of profiling tool. And the first one is a memory profiler. And this is for monitoring the size of the different variables and objects being held in memory. And this is useful for spotting memory leaks. So sometimes it can happen where you make a variable which should be cleared out of memory, but it stays there. And if you've got a huge network and all of those nodes are creating something that's not deleted, that can be pretty bad. Or if there's objects that's a bit heavier than necessary. And then the second one of these is a CPU profiler, and one of the main things that these do is show how long, in a rough sense, the program is spending in different routines. And a rule that Rich taught me was the sort of 80% rule of, if your code is spending the majority of time in one routine, it points to an obvious place to optimize, and it might point to, say, a slightly bad data structure being used. So when I was working with Java, the Visual VM is a good profiler for that, and that's an example of what its memory profiler looks like over time. There's some pretty cool visualizations for Python and Rust, I think, called flame graphs, and these are telling you sort of how much is being spent in different routines. And there's also a more basic HTOP, which is a command line tool that's, I think, built into every routine, that every machine, and you can just quickly check how much memory is being used in your machine, and also which cores are doing work at that time. Then the second big thing that's been really helpful for the journey, and would encourage you to do, is find a programming buddy who can help you. So whether that's someone who's in the same boat as you, who's also just starting to write code, or if there's someone who's more experienced than you in programming, it's a very helpful exercise to sit down and go through your algorithm with someone. Have you heard of the phrase rubber ducking? And this is a phrase which I first heard when I moved into the computer science group. And the idea is that you go through your line of code and explain it to a rubber duck. But it's even better if that is a person rather than a rubber duck. But the idea is you go through as slow as possible in the different lines of your code, and you explain precisely what each line does. And that can be helpful because the act of explaining itself can help you to see what might be wrong if there's something that's scaling well. And then also, if you have someone who's a computer scientist, the longer you've programmed for them, sort of more eagle-eyed you can become for spotting some of these things. Like I was programming with a friend called Fabian, who works in Pometry, developing Raspberry, and he sort of almost immediately said, like, why are you using a list there instead of an array? And this sort of thing is super helpful. And then also, if you program with someone, you can end up with sort of bonus hacky skills from them that you wouldn't have even thought to look for. So learned some random keyboard shortcuts and terminal tools that were definitely speeded up my my journey in there. And then this is what it felt like programming with someone who was more experienced and who definitely helped show the ropes in this way. So just a final couple slides on what the bigger picture outcomes were for this experience, as well as the Motifs algorithm. So the Motifs algorithm itself, it went from the first time I ran it taking 24 hours. That came down to 12 hours after spotting one thing, then making a different optimization brought it down to 8 hours, and then finally down to 2 hours. And I'm still hopeful to get it slightly faster than that at some point in the future. I definitely can't take any credit for this part, but by talking through this with the Raftery team, we identified some other functions in Raftery that were slightly slow at the time, like getting a node's degree and neighbors, and managed to improve those, and also how the storage was working. Very recently, Raftery has actually been rewritten in Rust to try and improve the storage capabilities, and also to have a better integration with Python. And as having rebuilt it in this way, before we needed to use Azure machine with, I think, like 256 gigabytes of RAM inside to store Alphabay, which was about 200 gigabytes. It's now down to 4 gigabytes as a graph, so can be run on a laptop instead. So I think definitely a worthwhile journey, and of sort of improving this algorithm and what came up Raftery for it. So yeah, with that I say thank you for listening. And I'd love to discuss a bit more with you. These are just some of the people who helped make it happen. And if you want to give Raftery a try, we've now got it, I think, on pip, so you can just run pip install Raftery or have a look on the GitHub page for it. But thank you very much.
Thank you, Naomi. There are any question about this second part? That was really interesting. And a very good use of memes.
Thank you.
So if there are no questions, I maybe make a basic question.
Right.
I mean, if you haven't done any big data before, and you need to work on those kind of data, what are your suggestions? Especially if you don't come from, maybe from a computer science undergrad, and I don't know.
Yeah, for sure. This was definitely my position. I'd not come from computer science. My background was in maths. Actually, I'll stop the screen share so I can see everybody. But, so I think definitely some of the things about the data structures are a great precursor anyway for working with big data, because they're are useful for being able to express your program well, both in terms of memory, keeping all variables small, which becomes super important with big data, and making sure the routines run well. I would check if the university has any courses on big data tools. I think within the computer science department, I think at Queen Mary there was a couple of different courses for master's students and undergrads on big data for doing this. And then also I'm trying to think of, there's been some quite handy like free resources online for doing so. One of the earlier tools I was using, this was before, not for Raftery specifically, but I learned to use Spark, which can work in either Python or Scala. And that's a really good sort of intro to thinking about how you can break down a problem in terms of, say, if you're doing some pre-processing or data wrangling on some big data set before you turn it into a network, using something like PySpark or can be helpful for just getting those first steps into there. Yeah, I think that might probably the best to start.
Thank you.
I had a question on the type of like programming language are you using in there? Because you're talking about Java, we're also talking about Rust, you're talking about Python, so maybe if you can go, you can just say what's behind what you're doing now, because I mean, it changes a lot. Sometimes, like I see that I'm working on Python, but then, yeah, is it worth to change the programming language, like, I don't know, because I can rewrite the code, but it's gonna take a long time, so
Yeah.
you don't know.
No, of course, yeah. It's so a little bit of the background with Raftery was that it used to be written in a language called Scala, which uses Java in a sense as it works with the JVM, which is what Java runs on. I'm cringe because I don't know, I understand these things from a sort of rudimentary perspective, and but then we found that yeah, thanks Ben, Java Virtual Machine, and I think Scala was picked because a lot of large systems like banks, for example, use Scala for processing transactions, and it's good for distributed systems. But then we found in the last year or so that it's not great for memory, having control of the memory, because it has its own inbuilt way of deciding when to get rid of variables that you don't have any control over. So it's, yeah, we were having problems with going out of memory, and then also we found that people much prefer interacting with Python, and we want the tool to be widely used as possible. So we want something that interacts well with Python, which Scala did not. Everything was horrible trying to write Python wrappers for it. So now the Rust, on the other hand, is a little bit similar to C++ in how you interact with the memory on the machine, and that gives you much more control of and the operations for writing variables and things are just much quicker. But what I was going to say on that front is that some of the tools like Raftery, but also like GraphTool, are have these optimizations in the background. So whilst, for example, the core of Raftery is written in Rust, everything we have Python wrappers for, which I think is working sort of as well as just the Rust, using it directly in Rust underneath. And so it's not totally necessary to pick up those other languages.
I think it's
Oh yeah, sorry.
not to gate crash, but I think it's possibly worth saying that if you've written something in Python that you really like, it's like great to experiment with. It's surprisingly easy to take those ideas and like write a small subroutine in Rust. You can then, there's a library called PyO3 that you can then publish that straight to pip. So what looks like then a Python library is actually just like native code written in Rust that's then like available to just install and use with in Python. So we spent, when we were in Java or in Scala, we spent 3 months writing a Python wrapper. This one we wrote in 30 minutes. And it's like, I honestly, I did it when I was at Naomi's parents over Christmas, and it was like a Christmas present because it just kind of worked first try. So if you have a program that you're kind of like that you've written in Python, you probably can take like small segments of that and rewrite it. Yeah, I'm very pro Rust, but if you ever wanted to, like, if anyone has anything like this that they're sort of thinking about, like, just hit us up and we can discuss it.
Yeah, I fully agree, and I think also possibly coming into computer science from maths, the steepest learning curve altogether was learning my first couple of programming languages, because the Theta code base was written in Java, and that was definitely a steep learning curve just because it was the first or second that learned in, but then having learned the basics of Scala and Java, Python and Java, moving across to Scala wasn't so bad a jump, and then even Rust looked scary the first couple of times. I saw some source files on there, but then seeing it in context with some other examples, was able to write something similar just by sort of following code that was there as an example.
I see. But have you worked on Julia as well? Like you tried with Julia?
I haven't. I'm slightly curious. Do you work with Julia?
I don't but for example, Lina has, and there's been another seminar before that was talking about this, and it was like, yeah, just why don't you use in Julia? I mean, it's like Python but works as C. I mean, there's no point not using it, and I still haven't decided to make an effort to do.
I have some comments on this second part. So it's actually, I can totally relate to the whole procedure of how do you optimize because although I'm not really working on data, but we also need to do some simulation to verify our theory. And in the simulation, of course, we need to optimize the code so that we can push to a larger system. So indeed, in the process, there's a lot of choices to make, like which language to use, which data structure, or which representation of the network can mostly optimize overall the whole code. So I had this experience. So because I'm studying mainly on population, so in the simulation, the main task I'm doing is to find the largest connected component in the graph. So basically, I need to write it is called the searching algorithm on the graph. So basically, to start from one node and go through the connected links. So basically, I have two choices. Either I can choose the depth-first search or the breadth-first search. So initially, we choose the best depth first. And it seems it goes somehow wrong when I'm trying to do it on a larger system. It seems that there's a restriction on the depth of the recursion. So if over the depth, like 1,000 steps, or I don't remember, and it will explode, give you an error. So I've struggled with this for quite a long time. And afterwards, I learned how to write the breadth first search, and this problem basically solved. And there are some other questions like how to store the network, because like mathematicians always use the adjacency matrix. You just put the adjacency matrix there and you play with the matrix. But clearly, a full adjacency matrix, there will be an n by n matrix. So it's impossible to go to larger than 10, maybe 20K on your personal computer. So later I need to decide for our specific task how I can save this. So basically I choose a dictionary actually for the links and for the connections, which saves a huge amount of memory. And in the end, because of this algorithm, the searching algorithm is an iterative process, so you cannot parallelize it. And I need to choose a language which performs faster on doing loops. So in the end, I use Julia. All putting all this together, it makes a great improvement in the sense that I'm doing this task, and some of collaborators using some Python packages. The code will be simpler, but in the end, it seems on a larger system, my code will finish in minutes, and their codes need to run for hours to get exactly the same result. So so at the very beginning, my code also very slow, and after the painful but long journey, in the end, I find a good way to optimize the code and increase and optimize the performance. So yeah, I was just saying I can totally relate to what you said, the procedure of doing. And yeah, so try Julia. It's not a bad idea.
Thanks. I am very curious. That's really great to hear. I think it is such a satisfying process when you see that it's completed, and it's somewhat, however quicker it was before, it's like almost adrenaline of like.
I think it's worth saying that if anything the last 18 months have taught me is that no matter how fast you make your system, if it's not written in Python, people don't want to use it. That's my I would love that these super efficient languages get picked up, but it's hard to convince people to swap.
Yes, it's exactly. So, for example, for our collaboration, my collaborators only use Python, so I can't really, discuss the details in the code with them. So what we do now is I use the Julia code to run some results, which makes more type saving, and I send them the data I generate, and they can further doing some analysis on the Python there. So yes, indeed, because not many people using Julia makes the collaboration more difficult. That's the problem. That's a pain point now. I agree.
I need to run, chaps. It was lovely to see you all. Catch you later.
Hello, Richard, have you got a hand up?
Yeah, sure. That's just a little point that it never has been more easy to mix languages these days. So you said, it's true. Now, most network scientists won't touch anything that isn't Python, but it's never been easier to have the bit of your code that needs to be fast written in something else, which is the trick that Raftery uses. You interface to it with Python, but it's using the Rust at the lower level to get it working. And when I started coding, that was near impossible. But nowadays, it's not actually too bad. So this can sometimes be the answer, and I think it's the answer that Naomi's work is using.
Yeah, definitely. I think it's that might be an interesting point in itself, is seeing if you are building something that's you want to be used by data scientists or something, finding out which languages interface well with each other if you want a particular one as a backend, and then something like Python as a front end. Yeah.
Yes, I agree. It's very hard. Depends also what you want to do as well, I think.
Yeah.
Because if you are testing a new feature and or a new measure of anything of the system, but if you don't know if it works, is it my mistake? And so you want to go with the easiest way. So maybe want to have an example on Python, and then so that's why I liked what Ben was saying before, because I mean you try on Python, you like it, and then you move on to that subroutine on Rust. And that, yeah, actually I want to know what is that way to change the code into to wrap it. I don't know exactly how to wrap things. This is something that is not usually taught, how to interface two different languages. So maybe we're gonna ask the slides if you can, and we're gonna post it on YouTube. But it could be nice if you can give some resources. Maybe they are already in the slides. I was seeing some things. We can share with the others as well, like in our mailing list, these resources that could be very useful, I think.
Yeah, I'd be happy to put a list of some of the particular tools and things together. And
Yes.
I think there was so I wasn't involved in any of the like writing of the Rust core or the interfacing, but I gather that there are certain GitHub repositories for where people have made those interfaces, and I don't know how easy they are to use, but I think it's sort of fairly plugged in, and yeah, they might have some examples in there for doing so. Yeah.
Okay, so I think we can close the session. Thank you very much again, Naomi.
Thank you so much for inviting me into the discussion. Yeah.
And we are always looking for speaker, but also for public. So if you want to attend one of our seminars, we have a Twitter, we have a website. and you can join us whenever you want. So thank you
you.
very much, and bye-bye to all.
Bye-bye, thanks.
Bye, thanks. Ciao, ciao.